Welcome back to Physics 371 Online. I'd like to finish off our discussion of the multipole expansion by commenting on the specific forms that the monopole and the dipole terms take in this series. So, looking at the general formula for the electric potential in this multipole expansion format, we can write out the terms starting from n equals 0, and the first three terms, the 0, the 1, and the 2 terms, are respectively the monopole, the dipole, and the quadrupole terms. So the monopole term simplifies very nicely. If we just look at that integral, we're integrating rho d tau over the charge distribution, and that gives us the total charge Q. So the monopole term makes sense. It gives us the same kind of term that we would get if all we had was a point charge. The dipole term is a little bit more complicated, but it can also be simplified in a fruitful way, and it looks like this. Distributing through the 1 over 4 pi epsilon naught, we have this expression with the integral r prime cos theta prime times rho d tau. And remember, the cos theta prime comes in because this is the first order Legendre polynomial. And now what we can notice, if we go back to the original geometry, the vectors r and r prime, when they're drawn tail to tail, theta prime is the included angle between them. And so in an attempt to rewrite this term r prime cosine theta prime, we can start with the dot product. R dot r prime is r magnitude times r prime magnitude times the cosine of theta, and that actually should be theta prime. And so we can solve for r prime cos theta, and what of course should be cos theta prime, and from this expression here, dividing both sides by r, we get this, and r vector over r magnitude is r hat. So r prime cos theta prime can be written as r hat dot r prime. And so we'll take, in the next slide, we'll take this expression for the dipole term and make this substitution and then see what we get. So here is the expression that we can replace the r prime cos theta prime term with r hat dot r prime. And so just making a straightforward substitution gives that, but then we notice that this integral is over the r prime coordinates. It's over all of the charge distribution. So the r hat vector points from the origin to the point where we're trying to find the potential. And so that is not affected by the integration. So we can pull that outside the integral and write it like this: r hat dotted into this integral. And so this integral, we notice, is something that only depends on the property of the charge distribution. Every piece of the charge distribution d tau prime is assigned a vector position r prime with respect to the origin, and then rho is the charge density at that point. So when we perform this integral, we're evaluating something about how the charge is distributed within the charge distribution. How much positive, how much negative charge there is at different points. So because of that, we make a special definition where we say that that integral can be defined as what's called p, the vector p, which is the dipole moment of the distribution. So if we make that definition, here is the prescription for calculating that, and then that allows us to rewrite the dipole term as, looking at the last expression up here, r hat dot p over 4 pi epsilon naught r squared. And the r hat dot p can also be written, since r hat is a unit vector, as p times the cosine of theta, where theta now is the angle between r hat and p. So if we wanted to actually use this in a practical problem, we would set the dipole up as the reference direction. The dipole moment would point along a certain direction, and then the point out here in space where we're trying to find the potential is a distance r away from the center of the dipole moment at an angle theta, the polar angle theta, and so the r hat unit vector looks like that. And so this would allow us to find the electric potential at a certain position with respect to this dipole moment. One other important calculation that's done in the textbook is to take this expression for the dipole moment and use it to calculate the electric field. Because remember, the electric field of a dipole, electric field of any distribution, is minus the gradient of the potential. And I won't do that here, but you can easily see in the textbook that there will be an r hat contribution and a theta hat contribution to the electric field at this point. So just to summarize, the multipole expansion gives us a prescription for calculating each term in this infinite series. And all we need to know is the charge density of the distribution. Again, the reason that this can be useful to us is that each successive term will be smaller than the previous term because it's proportional to 1 over r to a higher power. And so if all we really care about is an approximation, then keeping just the first few terms will probably give a good approximation, especially when we're fairly far in distance away from the charge distribution. So I wanted to just finish that up, and I will see you in class.